Hello and welcome to yet another video on my channel. This problem is on relations, and we can see that there are two matrices given, MR and MS, right? So this MR is the matrix related to the relation R, MS is the matrix corresponding to the relation S. And we need to find out what is R inverse, S inverse, R union S, R intersection S, and S complement, and of course their matrix representations. And the relations R and S are from A to B respectively. Okay, set A is given, the set B is given, and we will get down to work immediately. But before proceeding in finding out what each of these five requirements are in this question, we need to find out what is relation R and what is relation S. So if you look at carefully the matrix corresponding to the relation R, you can see that the first row corresponds to the element 1, the second corresponds to element 2, the third row corresponds to element 3, and the first column is 1, the second column is 2, the third column is 3, and the fourth column is 4. All right. Now, based on this coordinate system, this Cartesian system, wherever there is 1, there is a relation. Wherever there is 0, there is no relation. So we can see that 1 comma 1 and 1 comma 3 are the relations for 1. For 2 belongs to set A, it is 2 comma 4. For 3 belongs to set A, it will be 3 comma 1, 3 comma 2, and 3 comma 3. 3 comma 4 won't be because that's corresponding to 0. Okay, let's now proceed to the second relation S. So you see the first row is 1, second row corresponds to 2, belongs to A, the third row belongs to element 3, and the first column is element 1, the second is element 2, the third is element 3, the fourth is element 4, corresponding to set B. Okay, so the relation S would be 1 comma 1, 1 comma 2, 1 comma 3, and 1 comma 4, because all the four columns in row 1 are 1. And then we have got 2 comma 4, right? And then 3 comma 2 and 3 comma 4. So that's it. We have got the relations R and S. Now, the first question asks us what is the relation R inverse. The relation R inverse is as follows. What we do is that we look at each of the elements and we reverse them. So if we have, let's say, an element A comma B belongs to R, then we'll convert that into B comma A. So that's very simple, right? Okay, so 1 comma 1 remains 1 comma 1, the 1 comma 3 becomes 3 comma 1, the 2 comma 4 becomes 4 comma 2, and 3 comma 1 becomes 1 comma 3, and 3 comma 2 becomes 2 comma 3, and 3 comma 3 remains 3 comma 3. Okay, also in the same manner, the second one, S inverse, is given as follows: 1 comma 1 remains 1 comma 1, 1 comma 2 becomes 2 comma 1, 1 comma 3 becomes 3 comma 1, 1 comma 4 becomes 4 comma 1, 2 comma 4 becomes 4 comma 2, 3 comma 2 becomes 2 comma 3, and 4 comma 3, sorry, that's 3 comma 4, right? The 3 comma 4, 3 comma 4 becomes 4 comma 3, and that's the relation S inverse. Now let's quickly write down what the matrix representations of these two particular relations, and then we'll proceed to find the other relations. Okay. Okay, great. So the matrix corresponding to the relation R inverse would look as follows. It will have 4 rows and 3 columns, right? So the 4 rows correspond to the 4 elements of B, 1, 2, 3, and 4. This belong to B. And the 3 columns represent the elements of the set A, 1, 2, and 3. These belong to set A. correct? Okay, now let's write down. So let's see, 1 comma 1 is there, so it is 1. 3 comma 1 would be the third row, first column, and then we have got 4 comma 2, that is fourth row, second column, and then we have got 1 3, that is first row, third column, and second row, third column, and third row, third column, right? So basically all the others would be 0, and that gives us the matrix representation of R inverse. The matrix representation of S inverse would be as well, four rows and three columns, right? So the four rows correspond to the four elements of set B, and the three columns represent the elements 1, 2, 3, which belong to the set A. Now, 1 comma 1 is an element, 2 comma 1 is an element, 3 comma 1 is an element, 4 comma 1 is another element, 4 comma 2 is one element, and then 2 comma 3 is one another element, 4 comma 3 is the last element. Okay, and the rest of the elements in this particular matrix are zeros, and that completes the answer for the R inverse and S inverse. All right, now let's try to move on and look at R union S and R intersection S, right? Okay, so let's see how we can do that, right? So R union S. Um, okay, so what we do is, just because of the lack of space, I would want to bring the R and S down here. So that is how my R and that is how our R and S are, right? Okay, so R and S are here. So let's write down R union S. Okay, R union S. Union means all elements in both the sets, right? So we have got 1 comma 1 from the first set, 1 comma 3 from the first set, 2 comma 4 from the first set, 3 comma 1 from the first set. Remember, all these sets are basically the relations. We have got set R and set S, right? So we have written down all the elements of the relation R, and then we'll write down all the elements of the relation S. But then 1 comma 1 is a repetition. 1 comma 2, we could write 1 comma 2, and 1 comma 3 is also repetition. 1 comma 4, that's new. Okay, 2 comma 4 is a repetition. 3 comma 2 is another repetition, and then 3 comma 4 is the last element. So this is R union S, and R intersection S would be as follows. R intersection S would be all the elements that are common. So 1 comma 1 is common in both the sets, right? You can see the blue double-headed arrow that I have drawn. 1 comma 3 is also same, belongs to both the sets. 2 comma 4 also belongs to both the sets. So 2 comma 4 and yeah, 3 comma 2 belongs to both the sets, correct? So 3 comma 2 is another element over here. Now if we now we need to write down the matrix representations M R union S, right? That would be a matrix. So again, see, this matrix is going to have three rows and four columns. So three rows, 1 2 3, corresponding to the elements 1 2 3 of set A, and columns would be 1 2 3 4, corresponding to the elements of set B, right? Because R and S both are elements, both are not elements, both are relations from A to B. So A will be corresponding to the rows and B would be corresponding to the columns. So our union S, 1 comma 1 is there, 1 comma 3 is there, 2 comma 4 is there, and 3 comma 1 is there. You can notice that I'm putting 1 at each of the positions. 3 comma 2 is present, and then 3 comma 3 is also there, 1 comma 2 is there, 1 comma 4 is there, 3 comma 4 is also there, right? Okay, and the rest of them would be zeros. So this is our matrix for the R union S, and the matrix for R intersection S would be also having three rows and four columns, right? So each of the rows of R intersection S would correspond to each of the elements of the set A, and each of the columns of our particular matrix R intersection S would correspond to each element of the set B, right? So we have got 1 comma 1, we have got 1 comma 3, we have got 2 comma 4, and we have got 3 comma 2, right? All the other elements in this particular matrix are zeros, and that gives us the answer for our union, our intersection S. And finally, we need to find out what is S complement, right? So for that S complement, let's take down. So what I'm going to do here is I'm going to bring down the relation S, right? This is a relation S. Now S complement, mind it that S complement is a relation which is basically the uh, subtraction, the set subtraction A cross B minus S, right? And A cross B contains, what does A cross B contain? A cross B is the Cartesian product containing all the elements of the form small a comma small b, which is a ordered pair, such that small a belongs to capital A and small b belongs to capital B, right? Okay, now these elements, so this will contain all the elements. Let's see, 1 comma 1 will not be there, 1 comma 2 won't be there, 1 comma 3 won't be there, 1 comma 4 won't be there. Okay, let's try 2 comma 1, right? 2 comma 1 should be there, 2 comma 2 should be there, 2 comma 3 should be there, 2 comma 4 should not be there because 2 comma 4 is there in S. And then we have got 3 comma 1 and 3 comma 3, correct? Because all the rest elements are in our set S. And hence, now it's easy for us to write down the matrix representation of the complement of relation S, right? That would be again having how many rows? It will be having 3 rows, right? So 1, 2, 3. Each of these rows correspond to the elements of set A, and it would have 1, 2, 3, 4 columns, each of these columns corresponding to the elements of set B. Now let's write them down. 2 comma 1 is there, 2 comma 2 is there, 2 comma 3 is there, 3 comma 1 is there, and 3 comma 3 is there. And all the other elements in this particular matrix are going to be 0. And that is the answer for the matrix for the set, for the relation S complement. And that's it. Thanks for watching.